Erik received his bachelor's from University of California, Berkeley in 1995 in physics, and then he got his PhD in 2001 from UIUC in theoretical condensed matter physics, working with David Sepperly. And then he joined Lawrence Livermore in 2001, has been there since. And he's currently the director of High Performance Computing Innovation Center, and he's also the deputy director of the application development for the DOE Exascale computing project, which was developing application codes to run on the Exascale computing machines. And this is a project that's started in 2015. Right. Yeah. He's gonna talk to us about supercomputing at Exascale and beyond. One thing I want to mention is Erik is nominated as a Gordon Bell finalist for 6 times, and I don't know if anyone else, who has more number of nominations, and he won the Gordon Bell Prize in 2006. Yeah.
Awesome. Thank you very much. It's really a pleasure to be here. Not just because the reputation and the skill of the faculty and students of this department, but because I married a University of Michigan alum. So I've gotten used to her holler and go blue and anyone wearing anything with Michigan on it anytime we're out in public. So I have had my reverence for this institution kind of cooked in over 20 plus years. Thank you very much for that introduction. I also don't know if I could have done my own bio from memory, so I'm impressed by that. So I'd like to talk a bit about some of the experiences I've gathered, not just from the Exascale computing project, but also from my career at Livermore, in terms of the power of supercomputing and what one can do with it and why one should try to figure out how to do supercomputing, but also maybe where the difficulties are and what lies ahead. So I think we're in a very interesting period right now, which is good if you're a grad student and bad if you're my age. So, all right, let's see if I can make this quick. I think I need to read the scope. All right. Good. Okay. So the Department of Energy National Laboratory System has for decades hosted the world's largest supercomputers, and that trend continues today. I am showing some statistics that we like to brag about. We have been at the very top of the list for basically half of the last 25 years. Before that, it was every year. So the rest of the world has figured out how important supercomputing is starting to catch up, but this is still something we value highly. I'm just listing from there's every 6 months we put out, a list is put out internationally for the top 500. The top 6 computers are listed here, and you can see from the countries that this is no longer an American-only approach. In fact, the very tip top is in hot competition because this is an important capability for a variety of scientific and national security areas. All right, I'd like to start just with some broad overview stuff. If you understand, everything I'm saying might be super remedial, but I like to go to talks where at least the first few slides make me feel really smart. So I'm going to start low level and then I'll build up. But also, honestly, I think some of the things I'm going to talk about are things that they make sense, like you would have come up with the same exact thing, but you maybe didn't stop to put it in exactly the perspective of where we are right now. So if you do all your work on a laptop, I went to the Apple store and I spec'd out the most expensive laptop I could find, which is shockingly expensive, $4,200. But that is the 16-inch MacBook Pro with an M2 Max and as much memory as they'd let me put on it. If you look at our current fastest supercomputer, it has almost 100,000 times as much memory and almost 1 million times more compute. And I would actually argue quite a bit more compute than that because the flops in their specs are using their GPU, which is hard to use. So why do we build these monstrosities? It's because we want to do simulations that are bigger, that seems obvious, but also quite a bit faster, as well as more accurate. And that's, again, a very straightforward statement, but I want to give some examples from my career about how I've seen this in practice and how astonishing it really can be when you can take advantage of this extra capability. So this is something, again, super duper basic for most people, but it's also something that we don't always think about directly. So you buy a GPU for your home computer and it says it has 32 gigabytes of RAM and you're like, that's probably good. And maybe it makes it go faster, I don't know. But in the context of putting science on these machines, all memory really primarily means for us is the size of system we can stuff on there. And so I gave it the most simple example I could, which is take a carbon atom and represent it with numbers and how much data is that? That's like 52 bytes. If I buy the fastest AMD GPU, it'll come with 128 gigabytes of memory. But to map that into science, that means I can stick over 2 billion carbon atoms on there if I represent them in the most simple fashion in double precision. But maybe I'm doing circulatory modeling, and that's 4 million red blood cells with a specific model. So what we think of when we think of a supercomputer in memory, we think of capability and the ability to do systems at a certain size or a certain resolution because of how much data we need to represent that system. So the example I really like, and this is from a long time ago, 2005, I want to say. Yeah, there it is. So researchers at Livermore had been studying for a while some basic material science questions. And the one that we're going to talk about is their studying of how molten tantalum, liquid tantalum, would freeze under pressure. So you take a box of liquid and you squeeze it, and it would crystallize, but it would not crystallize into a single crystal because that's not how things work. It would have these different domains. But as they did those simulations, they did the biggest ones they could, but they saw that the size of the crystalline domains were about the same size as the box. So how can you be sure that's actually the structural property? I mean, that might be a goldfish in a bowl sort of situation where you're just getting what you get because your box is only as big as it is. So when we got our next big supercomputer, it was quite a bit bigger than the previous one. And so they were like, we're going to figure this out for good. And so I'm going to show you a movie of the biggest system they did, but we're zoomed in on the domains they were able to do in the past. And this gives you a sense of what you can really see physics-wise at different size scales. And so the color scheme here is, I believe the red are the crystalline and the blue are the liquid, or vice versa, but basically each color represents a state of matter. So that's really all you need to know for this. So we're going to start zooming out by 10 times as many atoms, which is a little bit more than 2x. And you see that solid domain is still about the same size as the box. So we do it again for another 10x. Again, it's much bigger, much more resolved, but it's still about the continents are still about the size of the box. And it's not until you get to 2 million atoms that we're starting to see structures that are fundamentally about the same size, no matter how much you zoom out. And so this is a slice through a three-dimensional simulation. They were able to then, not just look at one slice, but of course go through the box and make sure this behavior was consistent. I'll just let that finish. So again, very similar behavior. The grains persist, and then they rebuild in slightly different sizes and shapes, but very similar throughout as you scan. And so what we learn, I mean, we all knew this, but the only way to be sure that you're capturing the real physics of the simulation, that you're running a big enough calculation, is to run bigger and bigger ones until everything stays the same. And so same idea, but just sort of represented slightly differently graphically, that as you go to 2 million to 16 million, 2x in each three-dimensional direction, until the behavior really stops changing, you can't be sure you're actually capturing things correctly. So supercomputing really allows us to study things at a fidelity where we have confidence, and at a bigger fidelity where we can go back and look at the one we really cared about. All right, and then another super obvious statement, this is what people think about usually when they think about supercomputing, which is we can speed things up. Each calculation has a certain amount of work, characterized by the amount of mathematical operations you have to use to do it, flops. And again, this is just for the sake of the argument, this is ignoring the concept of memory. But if you were to do an hour of work on Frontier, that same super fancy MacBook would take 28 years to do the same amount of mathematical work. And that is, of course, not very efficient. So from the speed perspective, here's another project I worked on about 10 years ago. And it was an interesting one because it's really there was researchers at IBM who had been studying the concept of doing drug screening for toxic effects before these drugs get out into the population. And so one of the arguments they made is if you looked at drug recalls, what was killing people was more than anything cardiotoxic effects. I mean, some things were hepatotoxic, which is the liver, and there's other things that might kill you. But for the most part, our heart does not always react well to specific types of compounds. And you only find that out until you put it in someone's heart and then it stops. So what they wanted to do is model the heart at a very high resolution and high accuracy, and then they could turn the knobs on the parameters that control the heart behavior in the same way that a drug would, and see if arrhythmias would form. The problem was they had this great model, but it took them months to run more than a few heartbeats. And that's very hard to do a proper screening study because not everyone has a heart attack in the first 2 seconds of getting a drug. So they came to us, we've been doing large scale computing, and they said, can we speed this up on our new IBM supercomputer? And we said, yes. We hoped. But so this was an interesting one for me because I didn't know anything about cardiac modeling. I still don't really. But what we do know is give us equations and data, and we're supposed to break up that problem across a supercomputer. And honestly, a lot of the physics problems we'd solved had a very similar character to this, computational medicine problem. And so we attacked it in the same way. We used a lot of the tricks we'd used before. And rather than taking months, and we did have a faster computer at this time, we were ultimately able to do an hour of heartbeats in an hour and 7 minutes. And I always put the 7 minutes because we desperately wanted to get the exact real time, but we just couldn't quite get there. But what I want to show now is a movie of an arrhythmia forming in response to a specific drug. And you'll see that the structure really does require a full human heart with high resolution, because this is not a local effect. It really does require, it's a weird standing wave. And this is just the same heart from 6 different angles. And so you get these electrical signals that feed off each other and create this weird self-sustaining motion. And it's just because you've taken the ion channels in your heart cells and changed the way they open and close a little bit by putting a specific drug in your bloodstream. And so now you can actually look, you can put a drug in someone's fake, this virtual digital twin before we had that term, and just run it for a day and see, does anything weird happen? You could even stimulate it in a way that might cause a heart attack and see if it responds in that way. And that's a capability that wouldn't be possible if you couldn't turn this around so quickly. All right. So life has been good. We've been supercomputing for decades, but we are now at a transition point, and this is not driven by us. This is driven by the hardware marketplace. But for the longest time, we started with these vector supercomputers. If you've heard of a Cray supercomputer, that's what that was. But from the 90s onward, we mostly just did distributed memory parallelism. And this is what most people think of when they think of parallel computing. You write a code, you break up the pieces with MPI, and you distribute it across a lot of basically identical CPUs. It was a great time. Like your code, you might need to tweak it or optimize it for a different platform, but that was generally pretty small potatoes. Your code just ran from computer to computer. And ultimately, your real work was to figure out how to decompose the problem into pieces and not spend too much time communicating. However, it turns out that you can only make CPUs go so fast. Moore's law has come to an end. Denard scaling has come to an end. So it's just not possible to build a computer that uses a certain amount of power and does a certain amount of work that goes really much faster than they did 10 years ago. However, there have been other forces at work, and that's the fact that people like to play video games, and video games look better when things blow up in higher resolutions. So that market force has been pushing specialization and acceleration far beyond what CPUs have been able to do. Now, it was done just to draw triangles on a monitor, so very fixed work rates because you always had the same size monitor. But if we could harness that, we could go quite a bit faster with the same amount of electrical power. And so we are seeing that. That's become the standard engine for supercomputing, but it's much harder than it used to be because we now have two different things. We have a CPU and a GPU. They have different memory spaces. How you write code for a GPU that runs well is very different than how we used to write code for CPUs. And there's lots of the pitfalls that a code that seems like it should work may run into when it runs on a GPU. So we are in this new world. DOE has recognized this, and you can see it. I'm showing essentially our roadmap of all the big supercomputers we bought in the last 10 years. Back in 2012, we had one supercomputer at Oak Ridge that had GPUs in it. People who didn't want to use GPUs could just ignore it. There was lots of other big ones that didn't have those. However, by 2018, it was clear that all of our big machines were going to have GPUs in them, and we saw this coming. What really was tricky was the fact that we're a government entity. We can't just promise NVIDIA will buy their computers for all time because those computers will get incredibly expensive very quickly. And also we have to bid things. So very quickly, others got in on this game, and now we have supercomputers with GPUs from 3 different vendors in 3 different programming models. So GPU computing used to be, we were scared to do it on NVIDIA. Now we have to do it on pretty much anything that shows up. And so we found ourselves in a very different world than we really wanted to be. And let me just put a few more details on those last 2 supercomputers. These are our 2 exascale machines. The first is Frontier. It recently, just late last year, opened up at Oak Ridge. It's only recently, in the last couple of months, opened up for more broad access. I want to say April. But it is a true exascale exaflop machine in that it can do an exascale of double precision flops, not half precision machine learning flops like some other machines have claimed. It has almost 5 petabytes of GPU memory and an equal amount of DDR on the CPUs, and a little less than 10,000 nodes. So it's a massive machine. Aurora is the next one coming. This is being built at Argonne right now. Basically very similar stats, except the CPUs and GPUs are both built by Intel. This is Intel's first discrete GPU, which normally I would tell people to stay away from completely, but amazingly, the early ones we've seen are performing very well, so I will not say that. But be suspicious. However, just like I should have mentioned on the last one, that does not have you can't use CUDA to run on Frontier, and you can't use HIP, which is what you use on Frontier, to run on Aurora very well, although they're trying to make that happen. They have yet another standard for how you run on these machines. So we have 3 machines with 3 different native programming models, and that's a challenge for a scientist who really just wants to do work. All right, so DOE back in 2015 realized that we couldn't just sort of hope that all the scientists would get their act together and figure out how to manage all this hardware complexity. So we did something fairly unprecedented for us, which was we put a massive amount of money and time into software. Normally, software is something we just do, and we do it to do research. And if you manage to write something that could be used by someone else more than once, that's kind of a bonus. But for the most part, we really put it on the scientists to maintain their own software and to figure things out. We have realized with the complex hardware ecosystem we have, that's just not practical. And I don't think it's ever going to be. It's going to be practical anytime again soon. And so we had this massive effort. It did not, this $1.8 billion did not include the cost of those machines I mentioned. It's purely in the R&D and the software development needed to be able to use those machines. It used almost basically all the DOE labs, and it was broken into 3 pillars. So we had hardware integration. This was not the hardware itself, but people who would work with the vendors, work with the compute facilities, and make sure that we had the information, the application teams and software teams had the information they needed to make their codes use those machines well. Software technology was sort of foundational software, math libraries, programming models, Viz and IO type of libraries. And then application development, which is what I work on and what I'll be mostly talking about. And so, as I said, they broke into 3 pillars. And this is actually a really important thing because historically, when I wrote applications, the first thing I did was try to use as little of other people's software as possible because that was fewer things to go wrong when I was working on a new machine. If something I wrote went wrong, I could fix it because I knew how it worked. It really is no longer possible to do that and stay on top of things. If you want to run on all 3 of these GPUs and you want to use a sparse linear solver, writing your own, you're going to spend a lot of time supporting and porting and optimizing that. Much better to just use Hyper or Trilinos. And this story repeats again and again. So we have this dedicated pillar to developing that software and maintaining it. I'm going to talk a bit more about this in a second. And then, as I mentioned, this hardware integration pillar was really critical for us because physicists and application developers, they often are very savvy about hardware, but it's just things are changing so fast. It's really very helpful to have people whose job it is to sort of understand how a specific problem, will work on a given architecture and what needs to be done, to get around issues that are encountered. All right. So applications, we funded 21 open Office of Science applications and 3 national security applications. And they really spanned a wide range of fields. So we did very traditional things like molecular dynamics, like lattice quantum chromodynamics, plasma Wakefield accelerator design, but also things like seismic risk hazard assessments, climate modeling, metagenomic analysis. So it really was not just a wide range of science, but a very wide range of computational sort of characteristics in terms of the algorithms and the codes that were being used to do this work. And that was very purposeful because this project couldn't support every code that we care about or every code that's important for the nation. But the hope was if we did a diverse enough portfolio, one of these codes would be useful to almost any other application team out there in terms of watching how they did things and following their footsteps. And so that was the hope. So let me just give some statistics on this portfolio. each project had multiple codes in it generally. We started with over 10 million lines of code. I don't even know how many we wrote. I should probably find that out. But many of these were existing codes that had well-established capabilities. So we couldn't just say, delete everything and just start writing a new code. That would be easiest because they can't do that. They have capabilities that need to work in order for science commitments that have already been made to be completed. Also, it's just a lot of work to rewrite everything. One thing that was key is that almost none of these had ever run on a GPU. So at most, they had some OpenMP threading in there for CPUs. And the few that had only run on very small scale GPUs. Now, one thing that ECP did that I think is incredibly important was we did not just say, do your best to port to these architectures and report back. Or you have to get at least 50% of the peak flops on that machine or else you fail. We had to have metrics because we're a government project and that's how those work. But what we decided to do was, let's actually make success look like what we care about, which is how much science can you do on the Exascale machine compared to what you could do when we started the project on our petascale machines. So, however, that wasn't always easy for some of these codes because some of the projects we funded didn't really have a code to start with. Like the metagenomics project, they just had sort of some prototypical stuff they'd worked out, but they hadn't really put together a full massively parallel application yet. So we can't say make that 50 times faster because that is not really a thing yet. So we broke them into two cases. Our mature codes, our established codes, had to run a real challenge problem, a specific domain-specific problem that was vetted with subject matter experts in their field at full scale on the Exascale machine, and it had to go 50 times faster in terms of overall scientific work rate. So it didn't just have to go 50 times faster from wall time, that's very hard. But if it was 10 times bigger, it has to still go 5 times faster, for example. And then the other half had a capability metric, which essentially was the same thing, but without the performance piece. Define a challenge problem you can't do right now at a massive scale, run it on the full machine, and show that you now can do something you couldn't do before. So I'm going to talk a bit about what we've learned from watching these 21 projects go through this process. And one of the things I'm going to emphasize several times is you have to not think about this in terms of porting anymore, because things have changed so much that porting is really kind of the wrong way to go at this. And I know I said there's a porting component because you do have to do some porting, but this is much more about redesigning and rethinking things we've been doing for a long time with taking into account the new world that we live in hardware-wise and the world we're going to probably live in the future. And so first off, let me just talk a bit more about that science goal, and then I'm going to talk a lot about algorithmic innovation and the things we saw that really were most impactful for ECP. So, but first, as I mentioned, we needed everyone to define a real science goal. And I want to give an example of this because I think it's a really interesting example, which is one of our projects, they modeled wind turbines. But it turns out that, and this is at NREL, they have like a whole wind farm research center, which I actually went and visited, and they made me go up on top of one, and it was super scary. So the thing that's interesting about wind turbines is not only do you have to design the propeller and the whole system so that when the wind pushes it, it generates electricity as efficiently as possible. The fact is that each turbine produces an insane turbulent wake. So if you have two turbines stacked together, the first one is going to send the most jumbled, horrible air at the one behind it, and the one behind it is going to be constantly shaking. It's going to get very poor performance because these things do not exist in a vacuum. We tend to put them in fields. And so one of their big challenge problems was we can model a turbine, we cannot model multiple turbines. But if we could actually design wind turbine fields to minimize these effects, maximize the lifetime of these things, make them more efficient, and also just better understand the performance of this thing as an aggregate as opposed to as individual components. And so that's what they did. I'm showing a picture of one of their simulations halfway through the project. It is not their final challenge problem. And all that little crazy confetti is how they model the turbulent air, how they capture that in their own visualization space. So I put it up to this cool. I don't think it's super useful, for us to understand anything scientifically, but it does show just the insane turbulence that comes out of that first field. And before they can declare success, which they have recently done, they had to do at least 4 turbines in an array on a large field with a specific resolution and number of degrees of freedom, and that was their target. That had never been done before. We weren't certain that they could do it, but we would rather they failed. Our project metric is if it meant they were actually trying to achieve something scientifically meaningful. If they'd just done some metric of how many degrees of freedom can you do, they could have just done a super high resolution one turbine and who cares. So I think it's incredibly important when you're trying to make your applications run at the next scale up, that you have, your goal is not about performance metrics, it's about science metrics. You really want to be able to do something you otherwise couldn't do. And I think that's sort of obvious and cooked in, but when you talk to program managers and the like, it's never hurts to reemphasize, because I think they fought us a bit at first because it wasn't quite as quantitative as they liked, but they ultimately really got it, because this really is what we care about. All right, so algorithmic innovation. So first of all, you have to look at your algorithm. We want to use a GPU. And again, I apologize to those for whom this is super obvious, but using an accelerator is hard in large part because being designed to draw triangles on a monitor, the idea is the architecture itself inherently assumes that you're going to be doing a lot of the same thing at the same time. So SIMT, single instruction, multiple threads, is the architectural workload that they use. What you don't want to do is have a bunch of if statements in there, because now you don't have a lot of different threads following the same code path. You have some going one way, some going the other, and those have to be done then sequentially, and that's very inefficient. What's interesting is a lot of people really wish they could stay on CPUs. CPUs are actually in the same exact boat, maybe worse, because all the high performance CPUs now, to get the advertised peak performance, you have to use a massive amount of SIMD instructions, which is just like SIMT, except rather than when you diverge and you can't find all the same threads doing the same thing, they just do each one at a time. They don't even try and block it, they just give up. And so SIMD is also a case where we are seeing that our CPU machines now are very hard to use well. And the example I'll give is the Riken machine, or Fugaku machine at Riken. I don't want to throw shade at it, it's a great machine, but it's a half exaflop on paper. In practice, without a code that is very well optimized, it's a 64 petaflop machine. It's 8 times slower because the SIMD, it's 512 wide. You can't access all that floating point horsepower. So it's important to not just think, oh, well, GPUs are so hard, CPUs are so easy. Specialized hardware these days is pretty much equally hard. And it's because you have to find ways to turn all your code paths or your main code kernels into these things that are beautifully aligned and can be fed to the computer, fed to the compiler in a very easy way. Because compilers are really bad at finding SIMD because they can't take a risk on making any assumptions, because if they're wrong, then they give you the wrong answer and everyone gets mad. All right, so this is getting back to the point I wanted to make about porting. So the idea was, in the past, we had to have the same exact code and we'd run it on different machines so that we could very fairly compare the performance of machines. You know, LinPack is the most obvious example of this. This is our kind of main benchmark for measuring flops. But the quote here from Hennessy and Patterson, recent winners of the Turing Award, is that the problem with benchmarks is you are constraining the problem to the code and not what you actually want to solve. And what we should be doing instead is actually solving the problem and creating a real revolution and getting away from this concept that code needs to move from machine to machine to machine. What you need to do is look at the machine and solve the problem the way it is meant to be solved or can be best solved. And so I think that's a really important observation. But it's not as easy. It's easy to say, it's much harder to do. So when you're trying to reevaluate your code, you have to understand what GPUs want. And what they want is, as I mentioned, massive amounts of fine-grained parallelism. You generally shouldn't be trying to move too much data in and out if you can help it, unless you can overlap it. High arithmetic intensity is fantastic. Very few codes have enough for modern GPUs anymore. And avoid branching like the plague. All right, so let's see. Yeah, this is just another slide, essentially reiterating what I was talking about, but giving some examples from ECP on the types of algorithmic innovation that we saw. We saw a lot of people trying to get around the strong scaling challenges that they faced, using time averaging or ensembles. We saw people really trying to ramp up the fine-grained parallelism, and there's lots of ways to do that. One of the things I thought was really interesting was people who actually had to find alternative solutions just from the method perspective. So rather than using the simple PDE, the sparse linear system, they move to a higher order method or abandon Monte Carlo for a direct solve. And of course, you have to reduce branching. So to talk about sort of I think what a really great exemplar of how you really rethink your application, I want to talk about one of our applications that was tasked with doing small modular reactor modeling. There's people here at Michigan who work in this space or worked on this project. I met with some of them today, they're fantastic. But for those who aren't in the nuclear space, these types of reactors have been proposed, these designs have been proposed, but you really want to do computational modeling to get a better understanding of their characteristics before you build one and see if it blows up. I'm not a nuclear person. And so the key aspects of modeling it is you have to capture the fluids moving with a very turbulent fluid with a lot of particles flying around. So they use Monte Carlo for the neutronics and CFD for the fluid. And the Monte Carlo is the problem. So if you don't, I mean, this is again, I'm going back to basics, but Monte Carlo is one of the sort of fundamental ways of solving a simple problem. And so it's just, I've written some pseudocode on the right there of just, the most basic concept of Monte Carlo, which is do some stuff and then you sample. If this probability is greater than a random number, go down this path. If not, go down that other path. Do that again and again. So you're going to constantly, as you go through particles, they're going to be doing different things. So it's fantastically efficient for thermodynamic sampling. It really is one of our kind of core methods, and it was very popular. It moved from vector to distributed memory fantastically. Got great performance, got great results. However, as I mentioned with the thread divergence issue, moving to GPUs was another matter entirely. So this ExaSMR project looked at this, and they looked at all the branching in their code, and they're like, there's no way this is ever going to perform. And not only because they're branching, but they also have a massive load balance problem by the fact that some of those branches take a lot more time than others. So here's a histogram of particles bouncing around one of these reactors. And you'll notice it's a log scale, and almost everybody is in the far, far left in terms of how many times they'll collide before they're done. But you have these tails, which are orders of magnitude farther out, and each piece of some of those tails is a lot more computational work. So even if you broke your work up perfectly for a GPU, if that one particle is in that very expensive regime, the GPU is just sitting there while they wait on that particle to finally finish bouncing around and doing its physics calculations. So it's very inefficient, very, very poor performance. Instead, what you want to do is you want to parallelize the work that's going to all happen at the same time. And this is where they moved from what's the most natural and logical decomposition, which is parallelizing over particles, to doing that sampling up front and parallelizing over the events that result. And I'm simplifying, but it's a very clever idea. And it's super logical when you present it like this, but honestly, it makes a massive difference in performance. So they did this early in the project, so these are results on GPUs several generations back. But the thing I want to point out here is there are 4 different calculations, and they're all normalized to the first one, which is what they call history-based. That's the particle one. But as they started to redesign their code and add some other improvements, on top of that, they saw a 10x improvement in performance on the exact same hardware. And that's something I think that's the type of thing that we want to be looking for. Is don't just accept that poor performance on that architecture. Solve the problem for that architecture in a way that really takes full advantage of it. And they've done very well on the future architectures because of the starting point as well. All right, so porting, unavoidable. You do have to write code for the new system. And I think at this point I've kind of harped on this enough, but it is, keep the hardware in mind. Don't just take the code that you wrote for your CPU and write a bunch of CUDA and hope it works. But this is the question we get the most. People who've worked on ECP, who talk to people who haven't gone to GPUs yet, are going to ask you, what programming model should I use? And I don't have an answer. But I will tell you what the different applications use. And they basically fall into 4 classes. Some applications still live in I will write everything in the native programming model, and if I want to run on an NVIDIA and an AMD GPU, I will just write those kernels in the 2 different languages and keep them up to date. That is the worst approach, except for very specific cases, because you really have to then maintain separate code paths, and it's very dangerous. It's very easy for someone to implement a feature in one that they don't remember to port over to the other, or they don't test it on the other, And now you have a code that only kind of works, works differently on each machine. Loop pragma models are also probably the most well-known. You have OpenMP offload, OpenACC. It's very attractive because you just decorate loops, and then you're like, great, the compiler can do all the rest. I will tell a horrible story about how that doesn't always work out, but that is one that is a very popular approach. And one thing I'll mention is that for Fortran, that is in some cases the only approach. AMD and Intel have not shown a lot of interest in putting HIP and SYCL on Fortran, so OpenMP is kind of your only way out there. So if you have Fortran, that's what you should do. Otherwise, I would encourage you to consider the bottom row, which is the C++ abstractions. This is what NNSA, Livermore, Sandia, and Los Alamos have really bought into. And the idea there is using features of the C++ language standard, you can abstract away the execution to standalone pieces of code that can be written by computer scientists, and the physicists can stay up in the loop level. I'll talk a bit about that in a second. And then co-design frameworks was something we did in ECP, where if you are an adaptive mesh refinement code, what you can use is you can use the Amrex library, which, very low level, handles all the types of operations you would have for adaptive mesh refinement based, discretizations, implements them on different GPUs. But this is not the same as like an OpenMP, because your entire code has to be written around this, around this library. We call these co-design frameworks not from the traditional hardware co-design, but more from a software co-design. Your application and this capability have to be designed very, very closely together. And so if you're writing an adaptive mesh refinement code and you've never met the people who develop Amrex, I encourage you to do so, because that discussion and that understanding of what you're trying to do and how you're doing it is very important. Okay, so I mentioned the loop pragma models. I want to give an example of what that looks like in reality, because I think I don't want to say don't use them, but I want people to go in eyes open. And so the application in ACP where we really saw what this reality looks like was Quantum Monte Carlo. So the QMC pack code let out of Oak Ridge by Paul Kent. Fantastic piece of software. I did QMC as a PhD student. It's a fantastic method. It's very expensive. Anyway, so they decided their C++ code, they could have gone with Tokos and they did an evaluation, but they, in principle, were like, look, we do not believe we should have to solve this problem. There's an OpenMP standard, it is out there, and the vendors need to use it, so we're going to use it. So it was very, very stubborn. And so the most appropriate quote I found for their experience was from the movie Moneyball. And I'd watched it like an hour before I made the slide, so it was kind of, it was on my mind. But I mean, it is really true that if you are going to be the tip of the spear, you better expect some challenges, and they saw them. So I want to show the results on NVIDIA GPUs. I don't have their latest results for AMD, but I expect they're going to look somewhat similar. So the nice thing about them is they had already ported this to CUDA. So they had a working CUDA code that ran on NVIDIA GPUs. And so all the results I'm showing here, each block of bars is a different quantum mechanical system of atoms. So 16 atoms up to 512 atoms. And each of the, and they're all normalized against this CUDA code. So if you look at the left, that was their first result. And so for each one of these systems, they were about 10 times slower than the CUDA code, except for 512, which is only half as slow. This is not great, because this is the exact same hardware. You're using the model that they said they supported and the model that they provide natively, and they're massively different. However, they analyzed what was happening. They sent back feedback to the developers of the compilers and the runtime, and worked with the vendor. Thanks to ECP, they had a lot of leverage because the vendors cannot say that they were the big failure for ECP. And so they basically got them to put improvements into the compiler and the runtime. And so each of these bars is another version of the compiler and the runtime based on their work and their feedback and their reporting, them trying to analyze and understand why things were still going slow. And red was the final solution, which is an amazing result in that they are doing as well or better than the native compiler than the native programming model in at least a couple of cases. And for the largest systems, quite a bit better. So no one should say that OpenMP can't be great. And in this case, OpenMP is really great for them. They tend to do large systems. but it's not great out of the box and it's not straightforward. And this is with NVIDIA, which is our most mature GPU manufacturer. So AMD and Intel still uncertain. We are seeing some good results with Intel. AMD is a little more sketchy. But just be aware that the world we live in, HPC application developers do not have a massive amount of leverage. So you have to really work with people and do a lot of the legwork yourself to get things matured. All right, so just to kind of give a sense of where things are in ECP, most people are in C++. I'm actually showing the 2016 and the 2022 numbers of both of them, just because the only trend I saw change was anyone who could get out of Fortran did. Honestly, that's my advice. You can't always do it if you have a 30-year-old code. You can't throw that all away. But the vendors are just not showing a lot of excitement to support Fortran, and they are supporting C++. So just be pragmatic and get out if you can. I feel bad saying that, but it's true. But we also saw a pretty wide distribution in programming models. People did not just, it wasn't like Cocos is the only solution. It is a good solution, but people have made loop pragma work. They've made native GPU work. They just do the implementation themselves. And our co-design approach has been very effective, Amrex being the biggest success of that. And then, so I've mentioned integration and the importance of our software. I just want to reemphasize, don't try and do everything yourself. You really need to lean on the expertise and implementations of others. This is sort of a standard picture, just summarizing. I want to advertise that ECP has really tried to make things standardized and interoperable, the biggest being the E4S project. But within this project, ECP really tried to force the math libraries or the IO tools to converge on common standards and common practices in their software development so that it's as easy as possible to use them interoperably. And that has been quite successful. E4S is this project that we're trying to continue to support post-ECP. We're hoping it will endure. It's built on SPAC, which if you don't know about SPAC, go learn about SPAC. SPAC is the best way to install HPC software, bar none. It was developed by a very energetic guy down the hall from me at Livermore named Todd Gamlin. If you haven't met Todd, go meet Todd. He's a hoot. All right, so just to quickly summarize, I want to take a few more minutes to give sort of my thoughts on the future. So basically, I stole this from Andrew Siegel, who's the director of application development. I'm his deputy. This is really his entire philosophy in one slide, which is take the thing on the right and cross it out, which is this is not porting. Do not think of software as something you just use as a consumer. They develop an API and toss it over the fence at you and you use it. You really need to work with them to understand how to make your application interoperate with theirs well. And don't try and do everything yourself. That really is, and this is just sort of restating that in the positive. All right, oh, and I have a fantastic example of success. So this all sounds probably very torturous and like a lot of work, and you're like, I'll just stay out of HPC, it's probably easier. But this is one of my favorite examples from the application space, which is weird because they keep doing simulations of my house getting knocked down. But I'm kind of salty about it. They need to stop doing that. But anyway, so this is an earthquake modeling project that existed for years before ECP started. It was a very beautiful CPU-only code written in C by physicists. Beautifully done. Deep nested loops for a fourth order finite difference discretization. The problem is, by the time we got to the CPUs that had all that SIMD, they were getting a terrible percentage of peak. They just couldn't get SIMD because the compiler can't find it. So under ECP, they rewrote the code entirely in C++. They used Raja, which is the Livermore version of Cocos. They built in some data compression with one of the software technology libraries to minimize how much data they had to move around. And they made this thing go much faster. They also built in a coupling to an actual building model. So their idea is we're going to model some earthquakes, and we want to take that shaking and tie it to how a building will actually respond that we can give to an engineer. And so if they're going to cite a new skyscraper, they don't just have to go by sort of generic building codes that guess at the average behavior. They can say for the soil you're sitting on in this area, if an earthquake happened across the bridge, what would happen to that building? And I have some of their latest movies on Frontier Supercomputer to show this. So this is the San Francisco Bay Area overhead. This building is on the Hayward Fault. This building is probably in actually Hayward. And then the epicenter is right here where the star is. And what I'm showing here is the movie of them modeling that building motion as the earthquake evolves. And so it's colored based on the damage that they think would be done to the structure based on their structural model for the building. And so you see that as things are dissipating, it's maybe damaged, but it's not getting worse. But you can absolutely imagine how a much more sophisticated building model could be put in place. And you could truly re-engineer your building to respond to this exact type of motion. And this is something that was not in any way possible for ECP. They were able to get a 3500x, I was on the last slide, I didn't mention it, improvement in their total scientific work rate by all the work that they did. And that now means they can do this simulation for as long as they can do it at the high resolution that allows them to capture the frequencies you needed for individual buildings. Before, they could only do low frequencies, which are like bridges and giant pipelines. And so not only that, I mean, a one-off simulation is great, but they've got the time, their throughput down, how long it takes to turn around one of these simulations, that they can instead do 25. They can pick different spots along the fault. They can run this thing out. They can put a building in any one of those spots and say, okay, here are all the different places we think an earthquake can happen on this fault. Let's see what happens to your building in all those scenarios. And you can engineer it in response however you see fit. But you'll understand that it's not maybe a one-off. Maybe 90% of the time your building gets completely leveled, or maybe it's only truly if the epicenter is like next door and you're mostly fine. So again, this is a capability that I think really could make a major impact on safety and how we design our cities in our earthquake-prone areas like I live. All right, so this is just another one. They've started doing other faults. I would actually like them to move and do other areas, but they seem insistent on showing my house knocking down. Yeah, and so it's fundamentally, I mean, from the movie's perspective, it's just sort of a simple, like, image propagation, wave moving through soil. But the amount of data that they have to start with to get that soil model, and then the high resolution wave propagation calculation they have to do, it's really hard to capture in a movie, but it is astonishing. All right, in my last couple of minutes, I just want to talk about the future. I think a lot of people are looking at the exascale machines we have now and saying that's a big lift to get there. I don't know if I even want to do it. I don't want to run on GPUs. Well, you'll pine for the days where all you had to do is run on a GPU. So yeah, so we have GPUs already. The trends we're seeing, I mean, the market forces are pushing ML and AI acceleration above all else. That is going to exist. It's going to be the most cost-effective way to do that type of compute. The question is whether we can harness it for non-AI workloads. Remains to be seen, mostly because of the precision issue. We're seeing specialization. You can't wring much more out of CPUs or GPUs, honestly, from a power perspective, but you also don't need general purpose in all cases. Why aren't we building ASICs? We could maybe be customizing our chip designs or our node designs to capture the very specific workloads that we do. The challenge there is the fact that you now have to write your code so we can put data in the right places and use the right type of hardware for very different architectures. And that's a much bigger programming challenge. And then quantum, which will be here at some point. I did quantum physics, so I'm very, very skeptical of quantum, but I mean, I know we'll get there. It's just, I'm very skeptical that like the people who tell me we're gonna get it in a few years, I think that's maybe a little ambitious. But at some point it'll be here, a totally different way of computing, totally different way of coupling our computing. So I want to talk a bit about heterogeneity. Heterogeneous computing, and by that I just simply mean you're not just running on a bunch of CPUs or a bunch of GPUs, but in fact you have, this is a summit node where you have a bunch of GPUs and a bunch of CPUs. You have to maybe do some work on one, move some work on the other, move things around. It's hard. You have to manage different memory spaces. You can't accidentally try and call a pointer that's not active anymore. And of course, you're operating in different execution spaces, so that's more complicated from a compiler perspective. So how we do this in ECP is very simple. We move everything onto the high bandwidth memory on the GPUs, and then we go to the CPUs. So we don't do heterogeneous computing at all. This is where we live. And so we have not actually tackled the problem of heterogeneous computing, but if we move into the architectural landscape that I think we will, we're going to have to. And for one other example, oh yeah, so this is just what I was saying, which is if you want data locality, you just abandon the CPUs, which for current GPU machines, you're not losing that much. Frontier has like 1% of the flops on the CPUs. It's all in the GPUs. So, you know, that's fine. But we should not be doing this. So the example I'm going to give is not an ECP example. This is work out of Duke University. Someone I've collaborated with a bit. And so Professor Amanda Randall's group does circulatory modeling. And what they are trying to do is model things like cancer cells moving through the bloodstream and figure out where they're going to potentially create a secondary tumor. It's a hard problem. It involves large length scales. What you can't do is brute force because there's too many blood cells in your body and you're going over too long a distance. So they designed an algorithm to cover the region of interest around the cancer cell with very high resolution blood cells. And that's all on the GPUs, but they needed to move through this whole system. And so it turns out there's all that memory sitting free on the CPUs that they can use for the bulk system outside of that window. And just with a bit of coupling and being careful about managing your overlap communication, you get all that for free. It doesn't take any more time than just doing that window by itself. And so I think that's the type of thinking we need to have to harness our hardware to do much bigger and more interesting problems than we can do if we do everything just brute force on one piece of it. And so this, I'm going to skip this. This is just basically the ideas behind that decomposition and how you have to make sure you are scheduled. This is a scheduling problem more than anything, because as long as you're not holding up the GPUs, you can do whatever you want with CPUs. But you have to make sure your algorithm is designed so that there's no communication bottleneck or sync point that's going to keep those GPUs from sitting around too much. All right, final thoughts. This is an exciting and terrifying time to do computational science. It's not easy. It's not going to get easier. It's also an incredibly great opportunity for innovation, for people to make a massive difference. Trying to really move the needle in computational science 20 years ago was pretty hard. I mean, people figured things out pretty well. There is now a lot up in the air, and I think really fresh ideas and new re-examinations of past practices could yield huge dividends. So I encourage everyone in this room to be excited about that and to, you know, not be afraid to just throw away what people have done in the past and try something totally different, assuming your advisor agrees. So yeah, things are going to get much more uncertain, and we don't know where they're going. But I honestly think that you know, as a community, there's a lot of opportunities for us to work together and solve some of these problems together. So you know, national labs, we've been very insular in the past, and we're stopping that because we just can't. We have to work with everybody. So at Livermore, we're developing open source software. We're trying to really collaborate with people as much as we can. And you know, if you are aware of something we're doing that you're interested in, please don't hesitate to reach out to me personally, because I'd like to help build those bridges. So thank you very much.
Thanks, of course, a very interesting and engaging talk. Questions and comments?
Yeah, so as you know, we have a lot of students here, and workforce development is one of the big you know, things that we're trying to do and you're trying to do. So if students are interested in doing more in this field, I know the DOE has a lot of resources available. Can you summarize a little bit?
I will try. Yes, no, we absolutely do. And certainly reach out to DOE folks you know, because we're all very eager. But I mean, our CSGF fellowship program is probably our banner program. It's bananas competitive anymore. At PESC is a training program at Argonne for HPC development that is fantastic. More of these programs are cropping up. Berkeley has just started doing an HPC summer school. Livermore is trying to stand up a much more, well, a decent website for one thing, but a much more engaging and usable outreach platform in terms of how we show people how to do HPC the way we do it, either on the cloud or on sort of standard architectures. And that's been something we've been very bad at. We've only really talked to people who have accounts on our machines, and we think that needs to change. So I'd say all the labs are really recognizing how important it is to start engaging with students and not just wait till they come through our doors and hope they know how to do things the way we do them.
So I see you didn't mention anything about high bandwidth memory and when it's gonna come into production, so to speak. So any comments on that?
I wish I knew. I'm as an applications person, I tend to just wait and see what my wonderful colleagues at Livermore Computing come up with for us. But I mean, honestly, HBM is better performance than we really expected if we'd predicted 5 years ago. So it's, bandwidth is incredibly important. Latency is starting to become incredibly important, and that is not moving as fast as we would like. But yeah, unfortunately, I don't have any real specificity or answers. I'm mostly just a little bit anxious, but generally happy with where things are right now.
Refactoring algorithms to take advantage of that, would you suggest going in that direction?
Oh, 100%. I mean, this is the reason that everyone just puts everything on the GPU because that's what the HBM is.
Yeah.
I think honestly, most of our applications are bandwidth bound in some fashion. Almost nobody is getting true full arithmetic intensity out, and if they are, God bless them. But yeah, no, you really need to try and find ways to minimize your data motion and then hit the bandwidth as best you can.
Yeah.
Oh, sorry, go ahead.
Next, Siki. So the scientific work rate is very, very interesting. It's something we've thought a lot about as well. And I really like the fact that you had a challenge problem, right, to sort of define whether you made progress or not. One of the things that we found, right, is scientific work rate, right? I don't know how you defined it. I actually tried to see if there was a paper where you actually defined it. But oftentimes, right, if you have a scientific problem, right, the work rate is defined by, you get the answer, right? Someone has to then analyze the answer and then test a new hypothesis, right? That's the full sort of workflow. And so in that sort of scenario, right, and we found, you know, many of the same things that you pointed out, right, which is that making something go, you know, faster is actually doesn't actually give you that much, because you're bottlenecked by the human step of the rate of new hypothesis generation. Right. And so I wonder if, like, you know, through all these applications, did you sort of, you know, how would you think about this part of the problem? Because obviously, if it's 50 times better, great. But like, if the fact that your hypothesis generation is like, you know, as a certain rate, then even if you had it 50 times faster, yep, in some way, right, it may not sort of give you tangible benefit in the rate at which you get to the final answer.
No, it's a fantastic point and exactly right. So to be clear, we cheated a bit on the scientific work rate where we just mean the HPC work rate. So it's particles per second, degrees of freedom per second, you know, maybe with a complexity factor in there, so that if you do a system twice as large, you get credit for all the extra work. But what you're describing is what we talk about as workflow, and that is start to finish. And the HPC piece maybe used to take weeks, but now takes an hour. But if all the rest of it takes 10 hours, who cares if your HPC piece is twice as fast? We did start a project in ECP called Exawork to try and develop components to standardize and streamline workflows from end to end. NSA is working on this pretty hard, but we've found it's hard to generalize it too much, that it tends to be very domain specific. Like what materials researchers are doing with density functional theory lends itself to a very different workflow than turbulence modeling for hypersonics. So each community right now is developing their own, but I think we need to start being more efficient about kind of finding common tools, because it is where we spend the most time now, I would say.
So is this ECPA like a platform that we can just run our code on?
So unfortunately, ECP is ending, and I should have mentioned that in like 2 months. The software will exist at the DOE facilities and is also open source. So like the E4S that I mentioned is, you can pull it off a SPAC. You can go, if you have an account at Oak Ridge, you can access it there. And DOE is planning to fund the continued development of that. So that software should continue to exist.
Yeah, so you mentioned that you have like a lot of people whose job is to figure out how to encode efficiently across different platforms, different hardware.
Yep.
If I have like a piece of like my package, like my code, how does those people help my code run efficiently on different hardware?
Right. I would say the facilities are, the DOE facilities are your main resource there. So Argonne, Oak Ridge, NERSC, they are user-based facilities, and they are very eager to help pretty much anybody make code run well. And each one tends to be very focused on the architectures and machines they have, but often they will give you solutions that are portable enough, or at least give you a path for full portability. Unfortunately, I don't know of any resource where they will truly just help you make your code beautiful and everything. I mean, we haven't done it for ourselves for half our code, so. no one's that altruistic, but I would say, yeah, start with the leadership class facilities.
So it's like more heavily depends on the actual facility you're running your code on, and then the people there will help you.
Yes, it's just, and also they want those machines to be used efficiently. It's bad for them if everyone's running at like 0.1% of peak. They don't build those big expensive machines to have them not be used well. So they're kind of excited about getting codes to run well, but again, they're very sort of self-focused on their particular architecture.
Yeah, so you basically have to talk to their people to decide how much code you need to modify.
Yes.
So that okay.
And they can also point you to tools for like profiling and assessment to see where the biggest bang for your buck will be. And also maybe things like coalescing memory or data motion.
Got it. And the last question is, could you go back to the slide that you're saying, maybe for Monte Carlo simulation, it's better to parallelize over event?
Yes, I will. I'm gonna get my arrow key going.
Yeah, that slide.
Yep.
So could you illustrate more on like how like the event-based parallelization actually works?
Yep, as best I can, because this is not actually. I'm pretty sure there's at least one person in the room who understands this far better than I do. But because I had some really great conversations about these types of applications. But the basic idea, as I'm trying to illustrate here, is each one of these is a GPU thread. And let's say it owns a particle, and that particle in the simulation will sample. Okay, I've moved through this region, but I'm near another particle. Should the two of us collide and absorb, or should I maybe bounce off and go over here? And depending on which particle and where they are, they may go down a different code path. This might be the absorption code path. This might be the collision code path. And so each of these particles is having different executions on that in the code. And these are all GPU threads. So the GPU, when it has a warp of these, will say, well, I want to do this work and I want to do that work, but these guys are doing different work. So what we're going to do, we'll do all the yellow work first, then all the green work. Everyone's sitting around while this happens. And we have to step through these things sequentially. And so they are at least doing that work in parallel, but it's only that little bit of parallelism. And so the events, instead you'll do, and I don't 100% know how they do it, but they'll do all that random number sampling and figure out from the get-go, but probably on the CPUs, which particles are going to be in which parts of the code as they move through the system. And so we'll bundle that work up and send it in warps based on the parts of the code they're going to traverse. And so it's just a way of reorganizing your execution to match how the hardware is going to best handle it.
Thank you.
Yeah, sorry, it sounds super bizarre, but it works really well. I think it's one back there too.
I don't know whether.
Oh, go ahead.
Well, as a reviewer of an ECP project, I noted that the impressive performance improvements were measured without I/O. And that's not reality. So in reality, we have I/O. We didn't touch upon that, but I was wondering whether you can talk about the progress we make in the I/O systems.
That's a really key point. And actually, I will tell you, we would have measured them with I/O if the I/O system was in good enough shape for us to do it. The project timeline got really compressed at the end because of the supply chain issues and the pandemic that led to the machines being delivered about a year later than we expected. So we thought we'd have this like year and a half for everyone to work out and do science calculations, and we ended up having to kind of rush through it. And so we basically said you can do it without I/O. I/O, as you say, is a critical part of scientific work rates. The I/O systems on Frontier and Aurora, I would say, are still at the point where they are not going to really hamper you, but I think they're probably our last generation of that unless some major breakthrough happens. Because just the sheer amount of data, if you were to write all of memory to disk, that's a massive amount of data, a massive amount of time. And so if you take all the GPU memory and dump it to disk, I think it's still tractable, but I think it's not going to be tractable for much longer. So we are actually, I mean, many teams are already exploring this in terms of compression or in situ analysis, but I'd say it's still early days. So we didn't require that, but it's a key part of their work.
It's also not very sexy.
Nope. I gets no credit, but it's a really important thing.
Hello, thanks for this wonderful talk. I was just curious in your future slide, you did not mention any FPGAs and stuff. So I was just wondering of your thoughts on it and compared against GPUs.
No, I'm very excited about FPGAs. The challenge with FPGAs is just the performance per cost is really so far from GPUs. But the reconfigurability, I mean, we have people at Livermore and throughout DOE who've been researching FPGAs since they became a thing. And they have a massive amount of promise for true specialization, that you could take your kernel and you reprogram at the start of your loop and just, design them around that. So the performance results we've seen are really promising, but I think we're really far from it being practical for us to put them in a computer at the scales that we're doing. And so they've remained kind of a research area primarily, but I'm hoping that'll change because I would love to run on them, honestly. I will say people who do FPGA research have leaned toward the Intel programming model of SYCL because it's so compatible with OpenCL. And OpenCL is the only way to get on the FPGAs and GPUs kind of seamlessly. So
It's maybe a mean question, but is any of the ECP application thinking of using quantum computers or quantum devices?
yes, no one is thinking of that. Honestly, I think there's a lot of applications we have that would not use that well. Our quantum chemistry obviously is the most natural match. I mean, which does beg the question of whether you're really even computing at that point or just doing an experiment and mapping it to your problem. But yeah, no, I think it's still early enough that until people have any sort of prototype, they're not really willing to put too much time into that.
So I think we're out of time, so let's thank Erik one more time.